Pretty often, right?
Pretty often, actually, since the COVID-19 lockdown, we can't have face-to-face meeting and seminar. That's why after discussion, we think it's better promote all those activities online. Yeah.
It's a nice system, very nice system.
Yeah, very convenient.
Yeah, you don't have to travel. Save a lot of time. At the same time, information is exchanged. That's nice. So when Sean asked me if I like to give a presentation to this webinar, I immediately accept it. Right?
Sean?
Yeah.
I think we can start.
All right.
Yeah,
great.
Right now.
Yeah.
So welcome everybody to join the scientific and industry webinar series. Today we have a very popular and famous speaker. He will mention about the membrane extraction for lithium, isotope enrichment, and lithium recovery. So just let me briefly introduce Professor Tauher. He is the editor of desalination and the head of the laboratory for membrane material and separation technology at Shanghai Advanced Research Institute, Chinese Academy of Sciences. He is a recipient of the Newton Advanced Fellowship from Royal Society, and his research interests membrane fabrication, resource recovery using membrane extraction, and membrane distillation for osmosis, acid-base solvent resistant manufacturing. He graduated University of Twente in Netherlands. His supervisor is Matthias Wesley from the University of Aachen. So he has a very long membrane experience for last 25 years. So let's hear about his presentation today. Just for the housekeeping, so keep your microphone on mute, and if you have any question, you can post your question in chat. So this is the chatting, so you can leave your message or questions here, so we can communicate after his presentation all the question and answer. So please join me welcoming Professor Tauher.
Thank you, Sean. Thank you for your nice introduction. I would also thank Professor Huanting Wang and Xiwang Zhang. Thanks you for organizing this meeting. It's my pleasure and my privilege to give a talk today. I will first share my screen. So today I would like to talk something different about membrane extraction for lithium recovery and lithium isotope enrichment. The core information here is how to design suitable membrane materials based on semi-crystalline polymers, which has a solvent acid resistance, especially for membrane extraction. To people who don't know where Shanghai Advanced Research Institute is located, here's a nice photo. I will give you. This area is Shanghai Advanced Research Institute. Next to our institute, we have Shanghai Tech University. So the total part you see here belongs to Zhangjiang National Lab. It's a brand new national lab, just started 2 years ago. If you want to visit us, it's about 25 kilometers from airport, and you will be lucky if you come to Shanghai. You can visit Disneyland, about 10 kilometers away. Before I start about talking about the work, I would like to introduce about research activities in my lab we are doing now. We have 3 clusters. The first cluster is desalination. We have done a lot of research on forward osmosis, mainly membrane fabrication and osmotic dilution. We are also having been working on membrane distillation. Our interest is the interface of the polymer membrane and the feed water. We developed a sleep theory, which unfortunately I cannot talk it today. This is a brand new theory for understanding how superhydrophobic membrane is scaling and fouling resistant. We also do a lot of nanofiltration membrane for wastewater. The second part is the core of our activity, resource and energy. We are the first lab working on membrane extraction for lithium, also for isotopes. The third cluster is about biomedical and pharmaceutical applications. Basically, it's about how to make a dialysis membrane and sterile MF membrane materials. I was started with Chinese Salt Lake brine. The problem is how to separate magnesium and lithium. Then I will introduce membrane extraction and membrane chemical exchange. How to design polymer membranes for this application. I will give you some examples for lithium extraction from Salt Lake brine, and how to use membrane chemical exchange for isotope separation. It's very interesting to see this figure that China is producing and consume nearly 50% of the electric vehicles based on lithium-ion battery. But the raw materials are mainly from Australia and South America. In China, if you look at this graph, we have plenty of lithium, but it's mainly in Salt Lake brine. So to extract lithium out of this Salt Lake brine is crucial for the industry, the EV industry of China. Unfortunately, when you look at the brine, it's typically low lithium, has a low lithium concentration and has a very large magnesium lithium ratio. If you have a lot of magnesium, and that means conventional lime soda precipitation processes, which has been used several hundred years, I suppose. It's very basic chemical reaction, which is not practical due to cost. You produce a lot of solid waste, and this will give us negative environmental impact to the Salt Lake brine. For separation, the second constraint is the separation of lithium and magnesium. The bare iron radius of lithium and magnesium are very close, even hydrated radius. The only difference, large difference, comes from hydration-free energy. This give us some hint that we might not be able to use diffusion controlled separation technologies. Instead of use affinity controlled separation technology to achieve very high separation for magnesium and lithium. Third constraint is the ecological problem. I was lucky to visit the Salt Lake brine, which is in Qinghai province, many times. It's so beautiful. If you keep this in your mind, you will have to think of which technology you should use, which should be green, low energy, and low cost. After several decades of research and development, this is the state of the art of lithium extraction technologies for Chinese Salt Lake brine. After we pump out the brine from underground, we first remove sodium chloride and potassium chloride. Potassium chloride will be used as a fertilizer. So there are two basic concepts to extract lithium. The first is adsorption, electrodialysis, nanofiltration. This is to separate magnesium and lithium. But afterwards, we have the lithium enriched brine, which has very low, still very low lithium concentration. RO is being used to further concentrate this lithium. Even RO is not able to reach the lithium concentration of 3% to be able to precipitate by sodium carbonate to produce lithium carbonate. So evaporation pump has been used. That's a practice. Recently, we proposed forward osmosis, but unfortunately, forward osmosis membrane is still under development. The second concept to extract lithium is that using liquid extraction. So it's basically affinity based separation technology. For the first concept, we have a separation plus concentration steps. It is very highly energy intensive. But for liquid extraction, separation and concentration are in one step. And basically, the energy consumption is much lower. The problem for the separation of magnesium, lithium based on diffusion is the purity of the lithium carbonate. Final product, lithium carbonate is not high enough for battery. And commercial membrane, nanofiltration membrane has a selectivity of magnesium lithium about below 10. The best published paper in 2021 reached selective factor of 30. However, when you look at the liquid extraction, we have plenty of highly selective extractant available. And you have, we are working on this hybrid extractant. This extractant has a single stage selectivity for magnesium and lithium about 100. If I remember correct, it's about 170. So this is much more superior than the nanofiltration or electrodialysis membrane. And how liquid extraction works for magnesium lithium separation or lithium extraction? This figure shows that liquid extraction is basically consists of 3 steps. The first is extraction, then chemical exchange of lithium, magnesium. Finally, stripping. Every step, they have a separation capacity and as well as enrichment capability. So we can achieve very high separation factor and a very pure product. This separation is basically based on the selectivity of the separation is based on here formula. I put it here, but we have derived this equation. It's based on the extraction free energy of magnesium and lithium. The problem for this liquid extraction is because the direct contact of the brine and the organic phase, so there is a loss of organic extractant. From environmental concern, this is not green enough. I will address this green problem of this liquid extraction later using membrane extraction. So what I have to, because we talk about the chemical exchange, what is the chemical exchange? Chemical exchange is a very important separation technology used by isotope separation. I put here an example of lithium-6 and lithium-7 separation. The reason we talk about this is because these two materials are very important for nuclear fusion and nuclear fission industry. And if you look at the separation technology, as a large part of this process is chemical exchange. We have extraction, stripping, that's basically putting the lithium into the system. Stripping, we take out the lithium out of the system. We have a cascade processes. Each step is a single stage separation. So we put hundreds of cascade separation stages together. When we reach equilibrium, we can produce pure lithium-6 or pure lithium-7. This project has been supported by Chinese Academy of Sciences, and we are taking a very small part of this project. The research project we have been working on is called the Membrane Chemical Exchange for Lithium Isotope Separation using organic extractant. The total project has been 7 years, cost about 4 billion RMB. For magnesium and lithium separation and isotope separation, if you look at the two process flow, schematic process flow graph, they are basically the same. In principle, they are the same. The nice part of this technology is that we have models available to precisely simulate the concentration and the targeted ion concentration, the productivity of the technology. And here I deleted 20 equations, but it is so beautiful that if you look at all the membrane processes, the chemical exchange is so beautiful because we can model it, simply model it. I will show you later. And we talk about the extraction and the chemical exchange. We put a chemical exchange as a core separation, core separation stage in the liquid-liquid extraction. And chemical exchange, what is chemical exchange? Chemical exchange is not extraction. I put here a frame like this is for extraction, this is extraction, this is for chemical exchange. This part is for magnesium lithium, this is for lithium isotopes. So for extraction, which means that the extractant is not saturated or is not in equilibrium with the brine. So there is metal lithium coming from the brine to the organic phase. But for the chemical exchange, which means that the organic phase and the aqueous phase, they are in equilibrium. So if there is one lithium coming from aqueous phase to the magnesium, to the organic phase, which means that the magnesium will coming from the organic phase to the aqueous phase. This is the same for lithium isotope separation. So keep this in your mind that the chemical exchange is purely for separation, is not for taking out of the product. What is the membrane extraction? It is so simple that when we put a membrane barrier in between brine and the organic phase, we have a membrane extraction. For this system to be stabilized, to stably operate, we need a solvent acid resistant material, which is resistance in any kind of organic extractant. We need a hydrophilic nanoporous membrane, which is permeable to ions only. We need a low diffusing mass transfer resistant membrane, and as well as a mechanically stable system materials. This is a chemical extraction system reaction for the system we use. I'm not going to detail about this chemistry in this talk. I was lucky or unlucky. I have been working on membrane extraction since my PhD, starting from 1997. I have been looking at the development of the supporting liquid membranes. And here today, I figure that only nanoporous hydrophilic membrane, which is organic and acid stable, can be used for membrane extraction. This is really reason we select semi-crystalline polymers. Why we need a hydrophilic membrane? There is a cartoon here shows that for a hydrophilic polymer, hydrophilic membrane, the lithium ions diffuse by ions together with some water molecules. But for the organic weighted membrane, because the lithium is conjugated with the extractant, it became bulky, so the diffusing coefficient will be low. This is the reason we select the hydrophilic polymer membrane. Why nanoporous? This is the young Laplace equation give us a liquid entrant pressure for the organic to enter the hydrophilic membrane. So we need a very small pore to block the entrance of the organic extractant into the hydrophilic polymeric membranes. But because we have a nanoporous membrane, the resistance of the lithium of the ion diffusing will be high. So how to increase the reduce the ion diffusion resistance? We need an interconnected porous structure. We adopted a structure parameter from forward osmosis. This figure shows that nanoporous interconnected pore structure, porous membrane we use for membrane extraction. To develop an interconnected pore, there is a model called two-stage demixing model. I will give you a brief description how this works. We started as the initial polymer solution. So when we have a liquid-liquid demixing or liquid-solid demixing, you will form a polymer lean phase and a polymer rich phase. So at this stage, when you remove all the solvent, you will get a closed pore or cellulose pore structure, which has a large structure parameter. But when you have at this stage, if your polymer rich phase has two immiscible polymer pairs, they will start to demix. So this is the second stage demixing, which will break up the polymer rich phase to give you a interconnected pore. There we will reduce largely the structure parameter. To select these immiscible polymer pairs, we have two choices. Or either we have a hydrophobic blend, but the Flory-Hodgins mixing model tells us there is a very limited selection of this type of polymer pairs. But there is another choice is a block polymer. We could have a hydrophobic or hydrophilic blocks, so they can demix at a certain state. The first trial, we have done this 10 years ago, is to select polyethysulfone and polyphenyl acetone, softenated polyphenyl acetone. The two polymers are rather miscible in certain state. The membrane we form is really has an interconnected nanoporous structure. And we have tested the membrane for lithium extraction. It works fine. You see here, the flux is as a function of the lithium chloride in the feed. But unfortunately, this polymer membrane is not stable in a large variety of organic solvent. So selection of the our selection starting from another polymer. This is called polyethyl. We were lucky to figure out this polymer because of the research work from Imperial College from Professor Livingstone. They have done a research on PEK membrane for solvent-resistant nanofiltration. It has a really resistance to a large group of solvents. How to make such a membrane has not been systematically developed. And so this is our research. We started from thermodynamics to see how tolerable this polymer system is to water. Interestingly, PEK is soluble only in strong acid. The first is a sulfuric acid. The second mixture is a methane sulfonic acid. And it is very much intolerant to water. You see here the cloud point. You have a very little amount of water, the polymers start to be mixed. And because of the strong acid, PEK is slightly softened. And the demixing process has two characteristics. They could have liquid-liquid demixing. They also have solid-liquid demixing. Solid-liquid demixing is because of the crystallization of polyethyl acetone. the second methodology we have to use, we need to do is to analyze the kinetics of the polymer system in immersion precipitation. Let me see how this works. Yeah, here you see when we put a water next to a polymer solution, they will start demix. We analyze the distance of this demixing line against time. You will have you will measure the slope of the distance against time. The slope is called nominal diffusion coefficient. It's a characteristics of how fast the demixing is for the polymer membrane system. It's very surprising to see that you have only 50%, adding extra 50% polyethyl ketone. The nominal diffusion coefficient reduced 10 times. This is a very drastic phenomena for any polymer systems. And I will go to next slide. So if you look at the scanning electron microscope, the PEK membrane consists two parts. First is sponge-like part, which is really nanoporous interconnected pore. And the second part is a microvoid, finger-like microvoid. Finger-like microvoids is because of fast development of this phase separation process, as I showed you in the previous slide. And the nanoporous structure, we think it is because the two-stage demixing process, especially for the polyethyl ketone and the softened polyethyl ketone demixing in the second state. So we measure this mechanical strength of the polymer membrane. It shows that there is a crystalline in the polymer. It is really strong when you have when the 50 micron film is stretched, and the stripping of the lithium is also acceptable, but it reduced with the increase of the polymer concentration. But it increased with the lithium concentration in the brine. If sulfonated PEK can give us a interconnected pore, why not we add certain amount of SPEEK into the polymer system to control the pore structure? Solubility parameter of the two polymers indicate that they might be very compatible. We use highness enthalpy mixing criteria to determine the compatibility of the polymer. It shows that below a threshold, the two polymers are actually rather miscible. And our DSC measurement indicate that the glassy transition temperature of the two polymer mix shows one shift, which indicates that two polymers can be are compatible at a molecular scale. So again, the thermodynamic measurement indicate that when you add SPEK into the system, it became more water compatible, but still they are not tolerable to a large amount of water. Interestingly, we have seen that nominal diffusion coefficient of the polymer system in demixing reach peak at 50-50%, which probably is because the percolation of the two polymers during demixing. The crystallinity of the polymer film, if you look at this graph, reduces drastically when the polymer, when SPEK concentration increase up to 50%. At 50% above, the crystallinity of the polymer membrane, SPEK, PEK, drastically reduced to zero at about 80% SPEK, so it's zero, which means that the disruption of the SPEK during the second stage demixing to the crystallization of the PEK. And structure, same scanning electron microscope showed that indeed the polymer membrane became rather porous as well as interconnected, the pores. And extraction and stripping flux, the two figures show that at 50-50% ratio, we have the highest extraction flux as well as the stripping flux. Why this membrane shows the best performance at 50-50%? It is because at this ratio we have the lowest tortuosity. PEK is very robust, and there is another polymer system that's a block of polymer. We use selected polyethylene-co-vinyl alcohol, abbreviated as EVAL. EVAL consists of a ethylene block, which is a solvent resistance, and a ethylene alcohol block, which is hydrophilic. And this polymer is also very resistant to a lot of solvent. We use DMSA and the solvent for this polymer, but for THF and DMF and alcohol and a lot of toluene and benzene, acetone, they are very resistant. And we have done the stability test for 1,000 hours by checking the lithium extraction flux after the membrane is being taken out of the organic extractant. It shows a very stable performance, and the mechanical stability of the EVAL membrane is also perfect. But how to make this membrane? This is a scanning electron microscope of EVAL membrane we prepared in the lab. You see here, this is nanoporous structure, bicontinuous, but there's a micro voids in the polymer matrix. It reduces as we increase the polymer concentration. To control the morphology is critical for making such a membrane. Different from PEK system, we develop another technology or methodology to analyze this, how to control the membrane morphology. We use the temperature difference of the polymer solution to the bath coagulation temperature by control the liquid-liquid demixing and solid-liquid demixing. Solid-liquid demixing is because the crystallization of the EVAL polymer. We took the polymer solution and decreased the temperature of the polymer solution. You will see at here about 8 degrees Celsius, there is a peak here. This is because the crystallization of the EVAL polymer, and there we release some heat. We call this transition temperature as crystallization temperature of the polymer solution. If we can plot the EVAL polymer concentration against the crystallization temperature of the polymer solution, you will get a phase diagram as this. Now, by the blue line is the coagulation temperature. By shifting this blue line up and down, we would be able to control if the polymer solution is starting with liquid-liquid demixing, or they were started as a solid-liquid demixing. By control this, if we have, for example, we have here 22%, the TC of the polymer solution is below the coagulation temperature, which means that the polymer solution could initiate by liquid-liquid demixing instead of solid-liquid demixing. So we have a large microvoid. But for this polymer solution, you see here that the coagulation bath temperature is below the crystallization temperature of the polymer solution, which means the liquid-liquid demixing is largely constrained. Instead, the solid-liquid demixing is taking control. So we would expect a more less microvoid, a more interconnected nanoporous structure. Now, by taking membrane chemical exchange, I will introduce you how to use EVAL membrane for lithium isotope separation. Again, the membrane chemical exchange for lithium isotope separation, it consists of 3 steps: extraction, chemical exchange, and stripping. This is a photo of the system we built in our lab to be able to enrich lithium isotopes, especially lithium-7. We use centrifuge to take the extraction and also stripping. The middle part is the main part of the system. We use hollow fiber EVAL membrane module. The hollow fiber membrane, it shows here, is about 100 micron thick. It has pores, which is not really optimized, but fortunately, the diffusing of the lithium isotopes in the system is very slow. This membrane is insufficient to be able to use for membrane chemical exchange. This is the module we developed in our lab. It is about 1 meter long, and the diameter of 90 millimeter. It has a 5 square meter inner surface area. But when you look at it here, I have to tell you that it took us many years to develop such a membrane. It's really engineering work to find the potting material, find the solvent-resistant potting housing, how to make the module without any blockage of fiber, without any leakage. It really takes a lot of sweat. And this is I show here is because that I will show you some figures afterwards. I will demonstrate that we did a lot of modeling for membrane chemical exchange to be able to simulate the system. But I'm not going to details about this. To be honest, this figure took us 7 years. You will be surprised to see that. We based on our system in the lab, we started from lithium-7 abundance from 92.5. After 2 weeks, we reach a equilibrium. The system give us a value of 93%. 93% lithium-7 abundance. And I'm proud to say that this is the first membrane technology to enrich lithium-7 from 90.5 to 93% abundance. The work has been published last year in Fusion Engineering and Design. This graph shows that we can design the system based on our previous results. We can design the system. You see here, when you want to reach 99.9%, you need about more than 200 modules, 200 theoretical stages, which is slightly larger because our module is less than 1 theoretical stage. So we need about 280 meter long system to reach 99% lithium-7 abundance. Stability of the module is very important. The reason is that for isotope separation, it takes a long time to reach equilibrium. We calculated our system, it will take half a year. So how stable the membrane module in touch with the organic extraction is critical, is really critical. We put the module into the system, in contact with the organic extraction for 2 years, and we take the samples out. You will see here the extraction of lithium is very stable. This gives us some indication that the membrane, at least the membrane performance is stable. And we took the membrane sample out of this module. This module, remember, we measure the flux and the mechanical strength. They are quite, especially the mechanical strength, they are surprisingly stable. So all the results come to one conclusion that EVAL membrane is a very excellent polymer for membrane chemical exchange. But this, I'm not saying that PEK membrane is not an excellent polymer. PEK membrane is certainly also a good polymer membrane for membrane chemical exchange. I will summarize my talk today. So hope I can have convinced you that the membrane chemical exchange is a very versatile technology to separate very similar ions. And I have introduced you how to make a semi-crystalline polymer membrane, especially for membrane extraction, as well as for membrane chemical exchange. I introduced you chemical exchange as a powerful technology for separating similar ions. But at this stage, we are developing modules. Hopefully, we will have a nice module, very efficient module in the near future. To summarize the core information in my talk, here I showed you theoretical philosophy for separation of similar ions. This part is I took this part from a review article from Yale University from Professor Ilmenich. And it is purely based on the ion diffusing and some interaction of the polymer membrane and the ion size and pore size. And it's like competition of the rabbit and tortoise. But my philosophy is that for very similar ion pairs, it's better to use equilibrium separation instead of diffusing controlled separation processes. We submit this year a review article to compare this theory and this theory to GMS. And hopefully it will be accepted. If you receive my article, please don't reject it. Thank you very much. And I would like to take thanks to my funding agency from National Science Foundation China and the Chinese Academy of Sciences, Ministry of Technology of Chinese People's Republic. I also thank my young scientists, my students, for their hard working. Two advertisements. The first one is desalination. I hope everybody can submit your best paper, best work to desalination. And the second is about MEMDES 2021 in Shanghai. Hopefully, we will have it on site. If not, I will let you know how we will progress it. And if you are interested in membrane distillation, you would like also to check if this special issue is the best platform for you to submit your papers. And finally, I would like to answer questions. Thank you for your attention.
Thank you, Professor Tao. It's a very wonderful presentation, very informative, also a lot of information for lithium-related membrane chemical extraction. So very impressive, your research and your presentation. Also, yeah, I will make sure everybody do not reject your paper. Also, we will make sure your conference, MEMDES 2021, Shanghai, November this year.
Oh, yes.
Was special issue for membrane distillation. So there are a lot of information as philosophical your slide. Thank you for your great presentation. So it's time to have a Q&A. I look at the chat box, but nobody asked any question. Looks like you have a perfect presentation.
Yes, it's very clear.
For the first time. Yeah? Ever before we organized this seminar, nobody asked any question.
Shiwan has one question.
All
I
right,
see that.
Shiwan. Okay, now you got now. Okay, Shiwan, can you ask it directly?
I have put the question into the chat box, but I can read it out. So I think it showed a very, wonderful, interesting membrane synthesis method to control, the structure of morphology, and some pores, you call some large pores, and some are quite interconnected. I'm just wondering, is there an easy or convenient method to directly, to check whether those pores are interconnected or they are, closed or isolated or disconnected?
Xiwang, you ask a very interesting question. And so the first, I try to answer you. I try to convince you that I made interconnected pores. So the first direct observation is, I think, is the scanning electron microscope from different angle. When you make a cross section of the membrane, you could cut in one like this section. You could also cut this section. Then you can put the two, but there is kind of 3D reconfiguration of the scanning electron microscope structure to 3D. So there you can make this. But unfortunately, I didn't find such a facility in China to reconstruct this 3D structure.
Okay.
If I could have it, it's very direct observation. The second observation is, I think, to measure the structure parameter. And structure parameter, because structure parameter give you indication how pores are interconnected. Yeah. So I think there might be other technologies, but I'm not aware of it. But perhaps you can give me some hints. Thank you.
I'm struggling with this question for quite long. Yeah. My group also working on the Isoporous membrane. Even though you can create some beautiful pore structure, but we are not sure whether those pores are interconnected. Yeah. I think definitely I was if you find some good method, please share with me.
I will send you a message. The 3D reconstruction of the scanning electron microscope.
Yeah.
I know there's somebody doing this, but I couldn't find it here. I will let you know if I know who can do this.
Yeah, thank you.
Okay, so we have a next question from Professor Huang Ping Wang.
Thank you, Professor, for the great talk. I have a couple of questions. So when you talk about the way using solvent membrane exchanger, right, to extract lithium, the first question is about the solvent. So do you use a lot of solvent, and do you need to recycle the solvent? I guess that's related to the cost of the extraction process. That's my first question.
Yeah. Sean, do I have the answer now, or I wait for all the questions,
Now you
Sean?
can answer as much as you can until 12 o'clock. So we have 10 minutes, so we have a lot of time to discuss, and you can answer it. Yeah.
Okay. Yeah. So one thing, I can answer your question now, and I will show you one slide here. If you look at this slide here, that actually the organic solvent is really recirculating in the system.
Okay.
So we don't, if there is low leakage of the organic solvent to the brine, the solvent is in principle confined in your system. We are not going to lose anything in principle.
Right. So the solvent is circulate in the system. Yeah. So how do you get a solid out? Because for the lithium, for the lithium-ion battery, right? So you need either lithium carbonate or lithium hydroxide. So how do you get lithium out of the liquid, right?
Look, if you look at also this graph can give you some hints. From you see here extraction, chemical exchange for lithium magnesium. So we get a pure lithium to the stripping phase. In the stripping phase, we have acid. So basically it's a hydrochloride. So hydrochloride will exchange with the lithium inside the organic extractant. So we get a hydrochloride acid lithium chloride solution.
Yeah.
This is the product, but it's a semi-pro product. What we do is that we use evaporation to get the acid out. When we reuse the acid, we get a lithium chloride, concentrated lithium chloride solution. In the lab, we have done this research. We reach 20% lithium chloride solution. So when we have a lithium chloride solution, we can use it directly for as a raw material, or we can put some sodium carbonate.
Okay.
To precipitate.
Okay. Before evaporation, what concentration can you get?
We get a 20% lithium chloride.
Okay. All right. Yeah. And then one more question.
No problem.
You're talking about isotope, 7, right? Lithium 7.
Yeah.
So you talk about you mentioned the abundance. So, what is the abundance that you want to achieve? So the maximum you want to achieve. So for practical application, right?
Yeah. Can you see my screen now, Huanting?
Yes. Yes.
So this is the calculation. Basically, we will reach as high as possible. But for different applications, they are different. I will go back to another slide. Well, it's in the front. Hold on, please.
Yeah.
Yeah. If you look at here, we have a nuclear fission and a nuclear fusion. For nuclear fission, we really need a pure lithium 7 as a coolant for the reactor. The purity is about 99.95.
All right. Yeah.
For lithium 6, for fusing, we don't need such a high concentration. Normally 30%, 40%, that's enough.
All right. Thank you.
Okay, so we have 2 more questions from the chat box. So from the Laura In. So could you explain more about the modeling part, molecular level and large scale processes? So if you have a little bit of modeling part, very short, and then also if you can talk about the large scale process, looks like molecular level, large scale process was including some economic analysis for your technology, because you didn't mention about overall how economically viable for your technology using existing your process. So can you please share this one, how?
I think Laura is a very, very enthusiastic isotope person. So from molecular level, we need for the modeling of the processes, we need a very little amount of information about from the molecular level, like the extractant, the separation factor. I have one slide in the front that shows some of the data, some of the factors we needed from molecular level to simulate the process. It's not really straightforward, you are right. So we need from molecular level, we need a separation factor. This can be tested by liquid extraction. Efficient enrichment state. So this is you have to set some parameters. This is the target. And feed purity. This is what you have. Productivity. This is what you set target set. So actually the separation factor is from molecular level. For simulated processes, you need a module configuration. I show later here the state efficiency. So how efficient is your state in the chemical exchange per state? So the module, if you have member module design, this is from a larger scale. So after you have all the information, you can put into the model. The model is it's available. If you have time, you can go to this paper. If you look at the paper, you will. I think you can do it by yourself. You can make an Excel sheet, a spreadsheet, so you can calculate how much you can how much abundance you can enrich, what is the purity of the lithium you can get out of the system. Yeah, that's I think basically what I can say right now. If you want more details, you can send me email. Nora, I hope, yeah, please do.
Yeah, she said yes. Yeah.
Okay, great.
Okay, so next question is from Zikao Li. So he's asking the membrane is based on equilibrium separation. So his question is how fast is the separation process? How this will affect the total cost of operation? So can you please share that?
This is a very excellent question, and I dare not to say that this is the drawback of the equilibrium separation principle. Yes, the speed compared to a diffusion controlled separation process is slow. But what we can do is to increase the contact surface area. For example, we can use a larger extraction column. We can develop a smaller hollow fiber inner diameter membrane. So if you have look at the dialysis for as a artificial kidney, a small module has 2 square meters. So what we can do is to compensate the slow separation process by increasing the membrane surface area. That's a strategy we have to use. In terms of cost, this is basically because as Huanting asked that extractant will not cost much because the extractant will be reused. It will be circulating in the system. So this is another cost. Then the cost is operational cost as well as a module cost. Fortunately, EVAL membrane module is very cheap. It's much cheaper than, it's more expensive than polyethylene module, but it's much cheaper than polysulfone, polyisosulfone in terms of polymer cost. And the second is operational cost. Operational cost will not be higher than diffusing controlled separation technology, because here we normally use high pressure pump. For liquid separation, we use only low pressure circulation pump. I think we are still working on the cost issue, also carbon footprint issue by comparing to the 2 separation principles. The progress is not so fast, but this question is very important, and we will try to answer that very soon. Hopefully this year. This is a nice question. Thank you. If you still have more concerns, please send me email. We can discuss this later.
All right.
Okay, thank you, Professor.
Thank you, Tao. And then let us give him very big hand for his wonderful presentation. Thank you.
Thank
also,
you.
we have a final announcement for the next. Can I share my slide soon?
Did I talk? Yeah, I will try.
You can remove.
Yeah, Professor. Well, can you please stop sharing your screen so that Sean can share his?
Great. Thank you.
Just now.
Yeah, so we have next speaker from the Victoria University, Michael Duke. So he will talk about the novel separation technology application for waste reduction and resource recovery in the food industry. So 2 weeks later, we will have another scientific and industry webinar series. So we have an INSTEC conference next year, 2022, December. So please also just submit to your abstract. So thank you for your participation. And then we will share all the recorded video after this webinar series. So you can contact Sue, and she will organize how you can access the video. Thank you very much, and then we will see you in 2 weeks. Thank you.
Thank you. Thank you, everyone.
Ciao.
Talk to you
Thank you.
later. Bye-bye.
Thank you. Thank you.
Thanks.
Bye.
Bye.
Bye.